Stylepost created a library called Stylib, and it's very similar to the old toolkit we used. And Stylib won the Innovation Award in Control for its implementation of iStreams and iStream filters. Now, if we look at the README, what an iStream is a constantly updating stream of information that we can easily receive the data with just a .get. Look at iStream. See, it's just simply return a value of a value is double, which is get. And we can filter this information with filtered iStream. We apply a filter on it like low pass, whatnot. As I said right here, this could be automatically filtered controller inputs and it's particularly useful for PID. Now, if we want to get this data every couple of milliseconds, we can use polling iStream. This is particularly useful as well when combined with filtered iStream. And be careful though, because data can constantly update. So you have to be careful with using filtered iStream and polling iStream. But in general, these are the importance of iStream is simply to get data. And in a nice way too, as an object. We defined speed as an iStream as this, and now we can simply we can put speed.get and receive our data quite nicely. As I said previously, if an iStream is meant to represent a constant stream of information likes to update quite frequently. Now this is where polling iStream comes in quite handy. What polling iStream does, if we look right here, you add an extra parameter, and this what it does is it does a dot get every 50 times a second, or realistically up to 1000 times a second. But it just polls the dot get method at a constant speed instead of the user defining it by just using dot get. And this is quite important if you're constantly if you're if like if you have controller inputs, information likes to change quite a lot. So calling dot get might not be as reliable as just using a polling iStream, which just updates at a constant speed. But you also have to be careful too. See, the value can change when you call dot get, so it's important to be aware when you pull a stream. When I was talking about filtered iStream, you might not know what a filter is. In the case of a filtered iStream, it applies a filter on a bunch of noisy data. And usually for FRC, all you really need is a low pass filter if you're dealing with noisy information. But Scilab, you're able to use multiple filters if you like. It just ha so happens that low pass filter is quite nice. It does the job most of the time. And also delay is a pretty big factor with filters, but there's yeah, it just has a bunch of options like moving average, high pass and low pass filters. And you can also group these filters together if you like. It might provide interesting results. But most of the time, low pass filters are usually the best. If you know what a convolution is, you know that it likes to look at past values, and it is quite a good example of a filter that introduces a lot of delay. If we looked at a time moving average, which is a simple moving average, we can read a simple moving average where instead of averaging the past x values, average all the values given in the last x seconds. Already, that will introduce quite a lot of delay. Even a simple moving average that averages the past values, you're looking at past data while information is constantly updating. And there wouldn't be a problem with this if you have quite a small data set. But if you have a PID model, a PID system, you don't really have the time for that. About a simple moving average, it was analogous to a convolution or a sliding box, and that takes a lot of delay as you're looking at previous values. Now a low pass filter filters out high frequency data much nicer, but it implements a timer, and this timer also gets the time since each and every .get call. Now, if you have a high frequency, if you have a high accuracy input, this DT term is going to be smaller, of course, because dot get is going to be called a lot. And then we have a smoothing constant, or yeah, a smoothing constant. And this DT term, as I said, is going to get smaller with high frequency information. RC is a constant, as RC is a constant. It has something to do with circuits. I won't bother explaining with that. But as this A term is pretty small with high frequency information, and we return a value, this A, this this portion is not, it's going to be pretty small. It's going to weigh less essentially. Last value is for last value is previous inputs before last value is just like the last previous inputs, but this term is going to get small. But if you have low frequency information, DT is going to be pretty big. This term is going to weigh a lot more, and this your last value, or the value that you just had that was inputted before you had the filter applied, is going to change rapidly. But with high frequency information, last value is going to be pretty similar to last value. This what it returns is going to be pretty similar to before it was applied a filter. Now, as I've said previously, sometimes you want to filter out noisy input data for a feed-forward model or a PID model. Sometimes you want to use a low-pass filter for very reactive and unpredictable data. Or sometimes you want to use a moving average if you have a small data set and really like know that the error is predictable. But either way, Scilab makes it so you can set filters for set points, measurement, or outputs. And you can see in this class, this controller class, which uh, if we go to the feedback forward, which is the PID controller, the PID controller extends the controller, so the PID controller could also easily get these filters applied to. We look here too. For for each component of PID, there's also implementations for filters and error. But anyways, going back, a little bit of tangent. Stylelib makes it really easy, so you can just set filters for outputs, inputs, sorry, outputs and measurements and set point. Just has these methods readily available, which is quite nice. It goes to show you the importance of iFilter. Great example of an iFilter group usage. This is a set integrator filter. I won't go over the math behind this as I don't understand it myself, to be honest. But these are lambda expressions, and these lines simply set the range of the integral and the limits of the integral. It also shows you the iFilter groups, and iFilter itself can take in lambda expressions. What's also interesting is that there is in the control folder there is both a controller class and an angle controller, and otherwise the angle controller works the same as a controller, but it deals with continuous numbers or just like angles. Now to be honest, I'm not quite familiar with PID, and I could not tell you enough about continuous versus discretized PID, but Stylib deals with a lot of the complications of dealing with angles and continuous systems, and they have a angle file that has a lot of neat methods that make it a little bit easier to deal with angles. You can see normalized degrees, normalized rotations, normalized radians, and there's also caching. Can I see? Yeah, get angle from cache angle lookup table. The reason why there's an angle controller, as I said, controller.java this deals with discretized values. This is all I wanted to talk about in regards to Stylib. What I'm particularly fond of though is, well, the object-oriented programming. I mean, look, polling iStream implements iStream, filtered iStream implements iStream, and I don't even work in Java. I don't code in Java. I never use Java, but this is also readable to me because it's all just object-oriented programming. And I still know a little bit about public method static. Like this is all still understandable and readable to me. And that's just the wonders of ever C programming and object-oriented programming. Just because this is in another language, is also understandable to me. It's just the wonders of object-oriented programming. Everything stems out of anything. And the PID controller, extends controller, everything just comes back together. And it's all wonderful.